In this video, I want to introduce the chain rule. Actually, in Calc 3, it's the chain rules. There's not just one because there's a lot of different situations we might find ourselves in. Right. So here's the basic chain rule. Suppose you have z as a function of x and y, and x and y are both functions of t. So that would be if you had, some curve described in the plane parametrically. Okay. And because you have z as a function of x and y, and x and y as functions of t, you can think of z as a function of t. I think of this in terms of the graphs, right? Z equals f of xy, the graph is a surface, right? The vector function here is describing a curve in the plane. And so if you're talking about a curve in the plane, which you're then, for each point, applying the function f to it to get z, you're essentially saying, I think of the surface as an altitude function. How high are you? And it's not just how high are you anywhere. Now you're saying, I'm moving along a path, and I want to know how high I am when I'm along that path. So it's not just anywhere, how high are you? It's a path. How high are you on that path? So that's what this situation, this is the way I visualize it anyway. And because you're now thinking of z as just a function of t, you could talk about the derivative. For instance, as you walk along that path, how fast is your elevation changing? Right? Because you could be you could be on a very steep mountain, but if your path is cutting across the mountain, you might not be going uphill very fast at all, right? Of course, you might be going straight up the hill depending on the direction of the path. So there's a question of what is the slope along that path? And so what is the derivative of z with respect to t, where t is the parameter of the path? Well, the chain rule here that we have is going to say this, that the derivative of z with respect to t is the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt. Now I want to note that this is really very closely related to what we just did in the previous section with the total differential, right? There we had that the change in z was the rate of change in x times dx plus the rate of change in y times dy, where dx and dy are small changes in x and y. Now, if you just take this equation right here and divide everything by dt, you get the chain rule. Right? And this to me is very much related to Calc 1. Imagine that. Where we had problems related to differentials, and then in the next section we had problems related to related rates, right? Where you would have one problem that said, you've got a sphere of so big a radius, what if you change the radius by a little bit? How much does the volume change? That was a differential problem. But in the very next section, they would say, I've got a sphere whose radius is increasing at a rate of, and they tell you the rate that it was increasing. And the question is, how fast is the volume changing? It wasn't how much does the volume change, it's how fast is it changing? It was a matter of rate. But the problems were exactly the same. With one of them, you used the differential. And on the other one, of course, in that case, it would only be the first part here. And then with the related rate problems, you did it as the rate of change is the slope times the other rate of change. Right? And this was differential problem versus related rates. And that's how I see this thing right here, is it's essentially saying this is a related rate problem. The speed at which z is changing is related to the speed at which x and y are changing. And that relationship involves the partial derivatives of the function, of the altitude function. Let's do an example. I'm going to do this two different ways. So I've got the sine, z equals the sine of x times y. And the path that I'm describing will be x equals 2t, y equals e to the 3t. And I want to find dz dt. Now I'm going to do this two ways. I'm going to do this as we might have done it in a Calc 1 class, and how we can now do it in a Calc 3 class. So in a Calc 1 class, I can only deal with one variable at a time. So this x and y, I'm just going to replace them. I'm going to put the 2t in for x, and I'm going to put the e to the 3t in for y, and I get this. I get z down as a function of t. Now there's no partial derivatives at all. This is just take the derivative with respect to t. And so I'll do that. This is the sine of something, so the derivative of the sine of something is the cosine of that something, and then the chain rule says take the derivative of the inside and multiply by that. So the derivative of the inside, well, that's a product. So that I've got the 2t times the derivative of the e to the 3t, and then plus the e to the 3t times the derivative of 2t. And there you have the derivative. Now, you could leave it like that, but just because I want to compare it to something later, I'm going to distribute this in to those two, and I end up with 2t. This right here, the 2t times 3e to the 3t, I'm just leaving it again because I want to show something later. You could combine the 2 and the 3 to be a 6, but anyway, 2t e to the 3e to the 3t cosine 2t e to the 3t plus 2 e to the 3t cosine 2t e to the 3t. So that's how you might have done it in a Calc 1 class. But now, using the chain rule, I've got another way of doing it. And this is the chain rule that I'm going to use. So I need the partial derivative with respect to x. So looking at the function, where was it? It's just off the screen now. Let's put it right there. All right, so the partial derivative of this with respect to x is the cosine of xy times y, right? Because the derivative of the inside here, considering y as a constant, is just y. So there's the cosine of xy times y. dx dt, derivative of this, is just 2. And then the partial of f with respect to y is cosine xy times x. Again, right, we're taking the partial with respect to x. Sorry, with respect to y, x is constant. So that is the x cosine xy. And then dy dt is 3 e to the 3t here. Now this is a little on the odd side because I've got x, y's, and t's. I'm going to substitute things in now so it's all t's. So again, as I did in the first method, I substituted right away. Here I've taken the derivative first, and now I'm substituting in x is 2t and y is e to the 3t. So plugging that in there, I get this, which is precisely that. Right? I would hope that I get the same answer doing it 2 different ways if they're both valid ways of doing the problem. Anyway, but that's the chain rule. Now, I'm going to come back to this chain rule in the next video because this has a ton of really cool stuff that it implies. But I want to take a look at the diagram here first. This is one of the ways I think about the relationships here. Z is a function of x and y. X and y are both functions of t. Right? When you're talking about derivatives or partial derivatives, you're saying how fast does something change when I change something else, right? If I change the input variable, how's the output variable changing, right? Well, in a function of 2 variables, the output changes for 2 reasons. One, you could change the first variable, or you could change the second variable. Here, the situation we had was that z is a function of x and y are both functions of t. So just changing t has the effect of changing x, and it has the effect of changing y, both of which have the effect of changing z. So there's 2 reasons why z might change when you change t. And I trace those paths from z to x to t, z to y to t. And I put these little symbols in here. This is the partial symbol, and these are d's for derivative, just indicating to me because this is a function of 2 variables, I don't have a derivative, I have partial derivatives. But here, each of these was a function of 1 variable, and you do have derivatives. So to get from z down to t, you've got to do the partial of z with respect to x, that's this, and then the derivative of x with respect to t, that's that. And likewise, to get there through the y, partial of z with respect to y, that thing, and then the derivative of y with respect to t here. So that's that chain rule. Chain rule 2. Chain rule 2 is a lot like chain rule 1, except that I got more variables. Instead of having a function of 2 variables, I got a function of 3 variables. But each of those variables I'm thinking as a function of 1 variable. Right? So w is a function of x, y, and z, but x, y, and z are all functions of t. So you can think of w as a function of just t. And if w is a function of just t, then it has a derivative with respect to t. And you say, what's the derivative of w with respect to t? Well, the picture looks a lot like the one above. W is a function of x, y, and z. X, y, and z are all functions of t. These are partial derivatives, these are full derivatives, and so there's three ways now that t affects w, because changing t will change x, which changes w. Changing t will change y, which changes w. Changing t will change z, which changes w. And each of those, the effect is they all add up to the total change in w, and we get this dw dt is this root partial w with respect to x times dx dt. That's the first one. Partial w with respect to y times dy dt. That's this one. And the partial w with respect to z times dz dt. That's the last part. Okay. So this is chain rule very similar to this one, right? But one more variable. I think of this geometrically now, instead of an altitude function, I think of this as temperature function, right? The space curve here, the vector function, is describing a curve in space, right? And if the function w or f, whatever, is describing temperature, then you're like looking at a bug or a bird or something flying around in space, experiencing different temperatures, right? It doesn't hit every spot in space, it just hits along a curve. And when you're looking at dw dt, you're saying along that curve, how is the temperature changing? How fast is the temperature changing? This is a function of three variables, but being restricted to a curve in space, and then looking at how it's changing on that curve. And it's not just on that curve, it also matters, it's going to matter how fast you're moving along that curve, right? It involves dx dt, dy dt, and dz dt. That is, a slow-moving bird won't feel the same temperature change as a fast-moving bird. Even though they're moving along the same curve, one will experience the temperature changes more rapidly than the other one. Right? So it depends on how the function is changing, and it depends on how fast they're moving along the curve. So all of that is incorporated in this chain rule. Another well, not very different, but somewhat different chain rule is this situation, where if you've got z as a function of two variables, x and y are both functions of two other variables, same variable though, u and v, then you can think of z as a function of u and v, because if you're given u and v, you can calculate x and y. Once you have x and y, you can calculate z. So z is a function of u and v. Now z is still a function of two variables, so it doesn't just have a derivative, it has still two partial derivatives. It'll have a partial derivative with respect to u, and it'll have a partial derivative with respect to v. The diagram looks like this. Sometimes people draw it like that. I don't care either way. I get a little confused in my own mind here because it looks kind of like four things here, but it's just u and v written twice. It cleans it up a little bit, but anyway. These are all partial derivatives now. Z is a function of x and y. X and y are both functions of u and v. Everything here is partial derivative because everything is a function of more than one variable. So to get from z to u, I can do through x or I can do it through y. And so the partial derivative of z with respect to u is the sum of these two paths. So the partial of z with respect to x times the partial of x with respect to u. That's that first piece. And the partial of z with respect to y times the partial of y with respect to u. That's the second piece. And then, of course, there's the partial with respect to v. So there's two ways to get from z down to v. And that's these two, partial of z with respect to x times partial of x with respect to v. Partial of z with respect to y times the partial of y with respect to v. Right? So there we go. Now, this is a situation, actually, that you may run into more often than you think. Here's an example. I've got z is a function of x and y, being x squared plus y squared. The graph of that is a paraboloid opening upward, right? Sitting there, vertex at the origin. And then I'm going to use these two functions. X is r cos theta, y is r sine theta. Right? So x and y are both functions of r and theta. Now you may recognize this as polar coordinates. If r is the distance from the origin out to whatever point you're talking about, and theta is the angle from the positive x-axis out to that point, then That's polar coordinates, and the x and y coordinates can be calculated knowing r and theta with these formulas. So this is interesting to me because I can think of this now when I'm going to take partial derivatives of z with respect to r and with respect to theta. It's like, what's the derivative is how is z changing in the radial direction? Or how is z changing in the theta direction? Well, the theta direction will be like rotating. And I can probably even anticipate the answer on one of those, because if you think about this paraboloid, it is symmetric to the z-axis. It's circular cross sections, right? And so if I'm moving in the theta direction, I might expect to have no change in the z value at all, right? But if you move in the r direction, if you move radially in any direction, right, but just moving that one direction, of course, the parabola goes up, the paraboloid goes up, and so I'm thinking, well, this would look like a quadratic or something. Right? So here we go. Let's take a look. Partial of z with respect to r would be this formula: partial z, partial x, partial r, plus partial z, partial y, partial r. And here we go. Partial of z with respect to x is just 2x. And the partial of x with respect to r, so partial of x with respect to r, the theta is just a constant. So it's just a constant times r, so the derivative is just a constant. And then over here, I've got partial z, partial y, which is 2y, times the partial y with respect to r. Again, theta is a constant here, so this is r times a constant, and the derivative is just a constant. Plugging back in here, x is r cos theta, so that's plugged in there, times cos theta. And then the y is being replaced by r sine theta times that sine theta. Factor out the 2r, I've got cosine squared theta plus sine squared theta left inside. Of course, that's just 1. And the derivative of z with respect to r is just 2r. Likewise, now, if I look at the partial derivative with respect to theta, this is partial z, partial x, partial theta, plus partial z, partial y, partial theta. And partial of z with respect to x is still 2x. The partial of x with respect to theta, let me scroll back up here and take a look at that. Partial of x with respect to theta. R is a constant. So multiplying by a constant, this is going to come along for the ride. And the derivative of cosine of something is minus the sine of that something, right? So you got minus r sine theta for that partial of x with respect to theta. Likewise here, partial z, partial y is still 2y, and the partial of y with respect to theta is r times the cosine of theta. So that's that there. Substituting some stuff back in, the x is r cos theta, and the y is r sine theta. And then that's 0. Is that obvious? There's a 2r squared times negative sine theta cos theta, and here's a 2r squared times positive sine theta cos theta. So yeah, that all adds up to 0. So that's that. Now, the partial of z with respect to r was 2r, and the partial of z with respect to theta was 0, which I think we anticipated the 0. The 2r we could maybe have anticipated as well, because again, if you're thinking of this as polar coordinates, these are the formulas for converting polar into rectangular coordinates. The way that the other way around, x squared plus y squared equals r squared. If you know x and y, you can calculate r by x squared plus y squared equals r squared. So this thing right here could be converted to r's and thetas. In fact, it's just r's. Z equals r squared. Well, z equals r squared. Take the derivative with respect to r. Take the partial with respect to r. Well, that's going to be 2r. Z equals r squared. Take the partial with respect to theta. Well, there's no thetas in there. So it's just a constant. What's the derivative of a constant? It's 0. Okay. So there was the 2r and the 0. Now, there's even more chain rules. Because you could have z being a function of any number of variables, and then those variables are functions of any number of other variables. So, you might have 15 variables that z is a function of. Each one of those is a function of 42 variables, right? So there's all kinds of partial derivatives here. But to find the partial of z with respect to t1, you would say, well, I can go x1 to t1, x2 to t1, x3 to t1, x to however many to t1, all get you back here. The partial of z with respect to t1 is going to be the sum of all of those pieces, right? And then you say, okay, how's the partial of z with respect to t2? Well, there's going to be a bunch of paths to get from z down to t2. Take each of those paths, partial of z with respect to x1, partial of x1 with respect to t2, partial of z with respect to x2, partial of x2 with respect to t2, right? And add them all up. Right? Take all those paths, add them all up, and you've got the appropriate chain rule.